Remi had said that he would like to do a quick presentation on, let me see.
It's not highfalutin stuff. It's not at Ken's level, but
oh no, that's okay. Yeah, well, Remi, would you like to go ahead, sir?
Sure. I'm just completing this paper where I believe I don't generally get involved in these areas. I'm more concerned with the engineering physics, but I'm continue finding that I'm bumping up against what they say in textbooks. So one of the things that I'm concerned about with electromagnetic propulsion is the idea that I can push against the 0 points. And there's this whole contention of whether this thing is real. Yes, so in quantum mechanics, you respond to differences in energy, or you use normal ordering to get rid of this embarrassing term.
Oh, and Remi, I'm sorry for interrupting. Your camera is really blurry. I'm not sure.
Yeah, I was deliberate.
Oh, that was deliberate. Oh, okay. I'm sorry.
You don't want to see me unshaven.
I don't mean to pressure you.
Okay, I'll try my best. Let's try. Yeah, it's a bit better.
Yeah, there we go.
So one of the things is whether this 0 point energy is real, is a thing. Yes. As I said, in quantum mechanics, you deal with differences in energy, and you can make it disappear with normal ordering. Yes. But then there's a problem with general relativity, where you've got this huge magnitude of 0 point energy, which if you put it into the stress energy tensor, well, even if it is isotropic, the idea that the pressure from it would cause terrific expansion of the universe. So what I do, I'll just share my screen and I'll show you what I'm working on at the moment. I'm just completing the paper. I've already put it up, but there's just a little section I want to sort out. So let me just share my screen. Bear with me. There we go, share screen. Now, screen 2, this one will do. I'll bring up this. So this is a section I'm literally editing at the moment. I'll take you back to the start of the paper. I'll give you a very quick overview of what I'm up to. Essentially, what I'm trying to do, I'm trying to justify 0 point energy, yeah? Because it's this ethereal quantity that nobody quite believes in. So in the first part of the paper, I just go back to Pauli and what he said, where he tried to cancel the 0 point from the boson fields with the fermion fields, and he came up with some measures to do this. And it so turns out that zero mass fields will dominate this expression. So you can forget the fermion fields, if I'm correct. I'm not only saying that, people like Matt Visser is saying the same thing. Okay, I just run through some basic general relativity. And then I come up to this point. How do we put something which is 10 to the 120 orders of magnitude in the stress energy tensor? And I'm saying that if you look at, say, just a particle, by analogy, it's not tensor density, it's just a particle. When you look at this here, can you see what I'm doing on the screen? Can you?
Oh,
Tim,
I'm sorry. No, I can't actually. All I can see is your face right now.
Bugger it. Can you see the screen at all? No?
No. Oh, that must be on your other machine.
Hang on. I haven't clicked share yet. I haven't clicked share.
Oh, there we go. Okay, so it started. There we go.
There we go. Okay, I'll just run it again. So here's the brief of the paper, what I'm up to. Just the introduction, recount what Pauli's saying when he's trying to get rid of this embarrassment. He's trying to get rid of this 0 point. He's trying to cancel it with the boson fields, with the fermion fields, but you can't do that. Yeah, it's the massless fields are going to dominate. So basically, the 0 point is going to be determined by an expression like here in equation 5. So when you take it up to a cutoff, Matt Visser's saying you don't need a cutoff. He says it automatically falls out from Lorentz invariance. Yes. But let's just say you've got a cutoff of the Planck frequency. And when you run this integral, obviously you get very big numbers. You're getting something like 10 to the 111, 10 to the 113 joules per meter cubed. It's a huge quantity. And when you compare it to what the astronomers are measuring, they're getting an energy density of something like 10 to the minus 9 joules per meter cubed. So you've got something at least 10 to the 120 orders of magnitude difference. So what I'm trying to say, how can you possibly reconcile the vacuum energy of quantum field theories with the vacuum energy that's found in relativity? So by analogy, I appeal to the stress energy tensor for a particle. And what's telling here is, when you look at the term E there, which is the energy, you're dealing with, you're dealing with creation and ionization operations. So you're dealing with something which has got real energy, something exists. And the trouble with the 0 point, it computes something at 0 particle count. It's a fluctuation. It has no right, this is the tenet of what I'm saying, it has no right being present at the 0 order in the stress energy tensor. Doesn't make sense. So what I've done is just do a simple kind of Taylor expansion, polynomial expansion. It's two things at once. And then what I'm finding is that the 0 point energy can slot in at the second order term in the Taylor expansion, or third order in the Einstein constant, which is just the 8 pi g over c to the 4th, yes? And it appears to be just a bit of numerology, but when you do, you're finding that you're 10 to the minus 9 off, which is a hell of a lot better than 10 to the 120. Yeah, you're finding that your 0 point is a billion times too small, right? But I justify this. It's just a little bit of numerology at the moment, but it does have some method in the madness. Because if you look at this term in equation 12, you're dealing with a fluctuation. You're not dealing with this term here, where you're dealing with real energies, on the ladder operations where you create a particle out of the vacuum. That's something very definite. You're dealing with fluctuations. So running through the paper, what I'm suggesting is that vacuum energy should be some 10 to the 9 orders of magnitude higher. You've got extra degrees of freedom. So in the paper, I suggest it might be string theory. When you get down to these levels, you're finding extra degrees of freedom. You're finding dimensions compactified. Yes, extra degrees of freedom. What I've suggested here, and I'm making a toy model, is just to say that there's an interaction term between the modes of the 0 points. So here's the 0 point for a particular mode at, say, a particular frequency. I'm saying it interacts with all the other modes, and you're going to have some interaction term like this. And I'm showing it in figure 2 here, where the idea that as the electromagnetic wave fluctuates for a particular frequency, it temporarily becomes a dipole. And all the other fields are doing the same thing as well. So it's experiencing an averaging of all the fields from all the other fluctuations. So there's an interaction term. So what I'm trying to do is just to set up a very simple toy model. It's just Newtonian at present. Yes, so it's just a mass, a damping term, and then in the equation 15, and then a stochastic term, which is the random fluctuation from 0 point. Now, it's giving me results over a narrow window, which is to be expected. So I was just looking at it this afternoon. I'm just looking at my notes here. And for a frequency range of some 10 to the 22 to 10 to the 25, it's giving me a number of about 1 billion. So you might say that's just numerology. So what I have to do with the model, I have to make it relativistic. And ironically, contradictorily, this works at lower frequencies. And the way I see that is that because the effective mass of your 0 point for that mode is so low, it's able to be accelerated very fast by the effective field of all the other modes. Yes, so it's achieving relativistic velocities. So it's counterintuitive. It's the other way around. And then at the other end, at the very high frequencies, well, it's because I'm using this Lorentz-Abrams formula for for the radiation resistance. So I should be using the full Dirac model. So I'm going to toy around with these models, and I don't think it's entirely numerology. And I think you'll get this 10 to the 9 factor pop out across the range of frequencies, which have then established a direct link between the quantum vacuum or quantum field theories and general relativity. And once again, you don't put it in at the 0th order, you put it in the 2nd order. You put it in as a fluctuation. That's the only way it can make sense. So I might have hit upon something here. We shall see. Okay, so that I'll stop sharing the screen now. So that just brings my little point about what I'm saying about there might be a way that you can relate, get rid of this 10 to the 20 order magnitude, 120 order magnitude, which has been described as the most embarrassing problem in physics. Yes. Okay, that's it. So